We've been told physics has already figured out what reality is made of. But that doesn't seem to be correct, because even our best model only works for part of the picture. When you actually look at it, it explains almost everything, while missing most of the universe. So here's the real question. If our best map works perfectly, why is so much still missing? Physics, Consciousness and Reality. Dickie Dredd and Nigel Adams. And this is part 9 in the video series, and still on chapter 1, The Hard Science. And today we're going to talk about the Standard Model. So it's section 6 in the book, The Standard Model, Particles, Forces and Symmetries. So we've had relativity, bending space and time, and quantum mechanics shaking up the world with the very small. There's another piece of the canvas, the standard model of particle physics. Think of it as the best attempt so far to map out the basic ingredients of objective reality and the rules they play by. It's the recipe book of the universe. It's a truly amazing feat of human ingenuity, taking thousands of physicists many decades, and I can't express that more. It really is an amazing bit of work. At its heart, the Standard Model says the world is built from a handful of fundamental particles. You can split them into two families, matter particles and force carriers. Matter particles are like the Lego bricks. These include quarks, which combine to make protons and neutrons, which the constituents of atomic nuclei, and leptons, which include the electron, the thing buzzing around the nucleus in an atom. 6 types of quarks, 6 types of leptons, each with different flavours and charges. That's the kit. Then there are the force carriers, called bosons. These are like the glue, the messengers that tell matter particles how to interact. The photon carries the electromagnetic force, the thing behind light, electricity and magnetism, pretty much all of chemistry. Gluons hold quarks together inside protons and neutrons, the so-called strong nuclear force, and the theory behind that is called quantum chromodynamics. The W and Z bosons handle the weak nuclear force, the one responsible for radioactive decay and some of the reactions that power the sun. And then there's the Higgs boson, the one that made headlines a few years back when CERN finally found it at the Large Hadron Collider, which is by far the largest and most expensive experimental bit of kit in human history. The Higgs boson's job is to give mass to particles, but be careful. Common idea of it being a pervading substance like a syrup is not correct, plus it only accounts for a small degree of the matter of the particle. So without Higgs boson, the universe would be just a spray of light and or other zero mass particles, zipping around with nothing clumping together to form stars, planets and us lot. Put all this together and you've got a framework that explains pretty much everything we see around us, all framed in the beautiful language of mathematical symmetries. We'll cover that in a later section. Standard Model is astonishingly accurate. Predicts the outcomes of experiments to crazy levels of precision, sometimes matching reality to 10 or more decimal places. It's not just a theory, it's tested, hammered and proven again and again in particle accelerators. But, and this is a big but, the Standard Model isn't complete. For one, it doesn't include gravity at all. Einstein's general relativity sits outside the framework, glaring at it. The two don't mesh. Then there's dark matter and dark energy, together making up about 95% of the universe, which the Standard Model doesn't account for at all. And I'll cover that in the next video. It's actually an appendix in the book, but I'll cover that in the next video as a sort of aside, just so we know we're on the same page. Neutrinos, ghostly particles that flood the universe, also behave in ways that don't quite fit the model. And then there are other more exotic issues. Then there's the weirdness of why it all looks the way it does. Why 6 flavours of quark? Why 3 generations of leptons? Why do the particles have the masses they do? The Higgs contributes to mass, sure, but the values feel like numbers scribbled on a cheat sheet without explanation. So the Standard Model is like the best map we've got of the visible part of the city. It works beautifully for where it applies, but there are massive districts which we know exist but haven't charted yet. Physicists call it beautiful but incomplete. Still, without it, there'd be no understanding of chemistry or biology. It shows that the chaos of particles smashing about has a hidden order, yet it also whispers that deeper layers are still waiting to be uncovered. And here's where things circle back. If the standard model isn't fundamental, if space-time and matter themselves might not be the base reality, then maybe what underlies it all isn't another particle or field. Maybe it's something altogether different. So what this section really shows is that the standard model gives us structure, but not foundation. And if that's true, then what we call fundamental might only be surface level, which means the problem isn't just missing particles or forces, it might be that we're looking in the wrong way entirely. And if that's the case, what if reality isn't built from things at all? Next up, we're still on Chapter 1, the hard sciences, and we go for Section 7 in the book, the hunt for the theory of everything, unifying gravity. And just to let you know, the book has now been accepted by the printers, so hopefully we can get copies out pretty soon, and we'll get on a website and people will start ordering them, or just continue looking at the videos and don't bother.